As you've been writing Lewis structures, you may have noticed that it's possible to write more than one Lewis structure that satisfies all the rules. And so when this happens, we have to have a way to identify what is the most likely Lewis structure that actually exists. One of the ways that we evaluate Lewis structures is by the use of what we call formal charges. And so when several Lewis structures are possible, the most stable one will be the Lewis structure that has the smallest amount of formal charge and the one that places any negative charges on the more electronegative atom. And so in this video, we're going to explore how to calculate the formal charges, giving us a way to evaluate the validity of our Lewis structure. To calculate the formal charge on the atom in a Lewis structure, you take the number of valence electrons, subtract any lone pairs, and then half of the bonding electrons. So for instance, when looking at the formal charges on the atoms in CH4, here's our Lewis structure. And so the formal charge on the carbon atom, we have no lone pairs around carbon. All we have are our bonding electrons. Carbon has 4 valence electrons. It has 2, 4, 6, 8 bonding electrons around it. And so 4 minus 0, half times 8 is 4. 4 minus 4 is 0. All of our hydrogens are identically bonded. And so hydrogen has 1 valence electron. Each hydrogen here has 2 bonding electrons around it. 1/2 times 2 is 1. 1 minus 1 equals 0. And so the formal charges around each atom in CH4 are all 0. We see here the Lewis structure for carbon monoxide. And so when calculating the formal charge of carbon, we have our 4 valence electrons. We now have 1, 2 lone pair electrons on this carbon. And we have 2, 4, 6 bonding electrons. 6 times 1/2 is 3. And so 4 minus 2 minus 3 equals a formal charge around carbon of -1. The formal charge on oxygen. Oxygen comes with 6 valence electrons. In carbon monoxide, it has 1, 2 lone pair electrons. It also has 2, 4, 6 bonding electrons. And so 6 minus 2 minus 3 equals a formal charge on oxygen in this compound of +1. Now this is not an ideal situation in terms of formal charges, because we have a +1 charge on our more electronegative atom. However, this is actually the only valid Lewis structure for carbon monoxide. A couple notes on formal charges is that the sum of all of the formal charges on the atoms in a neutral molecule must equal 0. And the sum of the atoms in an ion must equal the charge on that ion. And so in the previous example, we saw the Lewis structure for carbon monoxide, and we calculated our formal charges to be -1 on carbon, +1 on oxygen, -1 plus 1 equals 0, which makes sense because the charge on carbon monoxide is equal to 0. If, however, we look at the formal charge analysis for the carbonate polyatomic ion, and we calculate our formal charges, on this oxygen, we have 6 valence electrons, minus 2, 4, 6, and half of these, so -7. The formal charge on this oxygen is equal to -1. This oxygen has the same bonding profile, so it will also have a formal charge of -1. This oxygen here, again, came with 6 valence. it has 2, 4, 5, 6. I'm just counting half of the electrons in the bonds, and so 1 each. So 1, 2, 3, 4, 5, 6. And so this oxygen has a formal charge of 0. Carbon came with its 4 valence electrons. It now has 1, 2, 3, 4 electrons around it. And so carbon has a formal charge of 0. And so when we add up all of our formal charges, we get -1 plus 0 plus -1 plus 0. So -2, which makes sense because the charge on the carbonate ion is 2-. And so let's go through the process to evaluate the best way to write the Lewis structure for hydrocyanic acid, which has a formula with 1 hydrogen, 1 carbon, and 1 nitrogen. We'll first look at a Lewis structure that places carbon in the central and look at the formal charge analysis, and then we'll look at the Lewis structure placing nitrogen in the middle. And so hydrogen, 1 valence electron, carbon 4, a nitrogen 5. So we have 10 electrons to work with. We place carbon in the middle. We've placed 4 electrons. We'll put lone pairs on our outer atoms. So now we've used 10 electrons. We see that carbon does not have an octet, and so we're going to go ahead and put these electrons into the center for a triple bond between carbon and nitrogen. And now every atom has an octet, and we've used all 10 of our electrons. So we would say that this is a valid Lewis structure. But now let's do our formal charge analysis. Hydrogen came with 1 valence electron. It now has 1 valence electron around it from this bond. So hydrogen has a formal charge of 0. Carbon came with 4 valence electrons. It now has 1, 2, 3, 4 around it. And so carbon has a formal charge of 0. Nitrogen came with 5 valence electrons. It now has 1, 2, 3, 4, 5 electrons around it. And so nitrogen also has a formal charge of 0. And so now let's look at what happens if nitrogen is central. So again, we start with our basic skeletal structure. Now we've used 4 electrons. We're going to place our other 6 around our outer atom. We see that now nitrogen does not have an octet. And so we're going to put these electrons in the center. And so we get a Lewis structure then, again, with a triple bond between carbon and nitrogen, but now nitrogen is central. And so we do our formal charge analysis. Hydrogen came with 1 valence electron. It has 1 electron around it, so hydrogen has a formal charge of 0. Nitrogen came with 5 valence electrons. It now has 1, 2, 3, 4 electrons around it, and so nitrogen has a formal charge of +1. Carbon came with 4 valence electrons. It now has 1, 2, 3, 4, 5 electrons around it. And so carbon has a formal charge of -1. +1 minus 1 does equal 0. And so our formal charge analysis would seem to be correct, as that is the overall charge on the molecule. And so the question becomes, what is the best way to represent hydrocyanic acid? And the best way would be what we have on top, with carbon as our central atom, because that gives us formal charges of 0 on each atom, which is a more stable configuration. We also see that in the other example with nitrogen central, we have a +1 charge on nitrogen, which is a fairly electronegative atom, so it really doesn't want a positive charge on it if it can be avoided. And so we do avoid that in the top Lewis structure. And so hydrocyanic acid will absolutely have carbon as the central atom. Now we're going to apply some of these principles to determine the most stable Lewis structure for SCN-. In SCN-, sulfur comes with 6 valence electrons, carbon comes with 4, nitrogen comes with 5. We also have an additional valence electron from our negative charge, and so we have a total of 16 electrons. And so we're going to start with carbon in the middle, nitrogen and sulfur around the outside. We're then going to place our valence electrons around our outer atoms. So now we have used all 16 electrons, but we see that carbon does not have an octet. Now here, we could actually do several different things. We could either take 2 of the lone pairs here from sulfur and put those between sulfur and carbon, forming a triple bond between sulfur and carbon, giving us this Lewis structure. We could also do the same thing with nitrogen and take 2 of these, place them into a triple bond, which would give us this electron configuration. And we have a third option, which would be simply taking 1 lone pair from each and forming 2 double bonds. This gives us 3 different Lewis structures, which are all valid. In each Lewis structure, we've used all 16 electrons. Every atom has an octet, but we can see that our electrons are in different places in each Lewis structure. These 3 structures represent 3 different resonance structures of SCN-. They are all 3 valid Lewis structures, but the electrons are in different places. Notice that the atom locations have not moved, but in all 3 structures, the electrons are in different locations, giving us differing numbers of bonding and non-bonding pairs on the sulfur and nitrogen in each different structure. And so let's go through a formal charge analysis for these. In each of these, carbon has 4 bonds going to it, and so carbon, coming with its 4 valence electrons, has 4 electrons around it for each structure, and so the formal charge for carbon is going to be 0 for each one. In our top structure, sulfur comes with 6 valence electrons. It has 1, 2, 3, 4, 5, and so sulfur has a formal charge of +1. Nitrogen comes with 5 valence electrons and now has 1, 2, 3, 4, 5, 6, 7 electrons around it, and so nitrogen has a formal charge of -2. +1 minus 2 equals -1. And so that formal charge analysis seems to work out, since the charge on SCN is -1. In our middle structure, sulfur comes with 6 valence electrons. Here it has 1, 2, 3, 4, 5, 6, 7 electrons around it. And so it has a formal charge of -1. Nitrogen comes with its 5 valence electrons and now has 1, 2, 3, 4, 5 electrons around it for a formal charge of 0. -1 plus 0 plus 0 equals -1. So this seems to also be a valid formal charge analysis. In our third structure, sulfur comes with its 6 valence electrons. It has 1, 2, 3, 4, 5, 6 electrons around it for a formal charge of 0. Nitrogen comes with its 5 valence electrons. It has 1, 2, 3, 4, 5, 6 electrons around it for a formal charge of -1. 0 plus 0 minus 1 equals -1, which is the charge on SCN-. And so this also seems to be a valid formal charge analysis. And so now let's compare the 3. In the top structure, we have formal charges of a +1 and a -2. In the middle structure, one formal charge on one atom of -1, and in the bottom structure, one formal charge on one atom of -1. That tells us that the top structure probably is not the most stable, as we have more formal charge distribution in that structure. And so we have to decide between the middle and the bottom structure. When we analyze the electronegativities, nitrogen is more electronegative than sulfur. And so the more stable resonance structure will be the one that places our formal charge on our more electronegative atom. And thus, the bottom structure is the resonance structure that we would say is the most stable. We will talk much more about resonance structures in the next video, but be aware that this is one of the ways in which we will evaluate resonance structures to see which one of them might be the most stable. And so in this video, we have looked at the concept of formal charges. Formal charges give us a way to evaluate different structures to see which one might be the most likely to exist if several different Lewis structures are possible for a molecule. I hope this has been helpful. Be sure to review formal charges in your book, and come see me for some extra help if you need.